Hello. In this video, I want to start to make the connection between the statistical mechanics we are just beginning to learn and the classical thermodynamics that we learnt during all the earlier videos. To do this, I'm going to explain how entropy enters statistical mechanics. Before we get on to that, let's first briefly review what we did in the last video, the video where we generalized the generalized partition function and the expression for the probability of being in a microstate. These are the two expressions shown on this slide. If you remember, we derived these expressions by minimizing the value of the information functional for our probability distribution subject to some constraints. We introduced a probability distribution that told us the probability of being in each of the microstates and required that the sum of all these probabilities would have to be equal to 1, as the system must be in one of the microstates at all times. The other constraints were on the average values of the various extensive thermodynamic variables. We noted that each of the microstates in phase space would have a value for the extensive variables, in this case the volume and the internal energy, and that we would calculate the average values of these quantities by calculating the summations shown on the right, on the left, and in the center here. In addition, we said that for the time being, we would write the general version of these two expressions using the symbol B superscript K underscore I to note the value of the kth extensive quantity of interest for microstate I. Having reviewed all this, let's now introduce the central notion in this video. In statistical mechanics, we set the entropy equal to minus the information as shown here. Let's consider what this means for a system that has a uniform probability of being in one of W different microstates first. As the distribution is uniform, all the pi values will be equal to 1 divided by W, where remember W is the number of accessible microstates. We can take a factor of 1 over W outside this sum as it does not depend on the quantity being summed. The sum then runs over the Wn accessible microstates, so we are left with K log W. At this stage, remember that when we first introduced this notion of information, we required that the uniform probability distribution has the minimum information. If we now consider the entropy, we thus have that the uniform distribution has the maximum entropy. Now, remember that in classical thermodynamics, the system, if it is in equilibrium, must be in a state that maximizes the entropy. If we think of the result that we have just derived, that the entropy is maximized when the probability distribution is uniform, this fact, that the system is at equilibrium is in a state where the entropy is maximized, is just a manifestation of the principle of equal a priori probabilities, which told us that an isolated system in equilibrium is equally likely to be in any one of the accessible microstates. If the system is equally likely to be in any one of the accessible microstates, the probability distribution is uniform. The information function has its minimum value when the probability distribution input is equal to the uniform distribution. And the entropy, which is just minus the information, is thus maximized. Let's now consider the more general case and work out the entropy of the system when we have some constraints on the average values of extensive thermodynamic variables. We know that the entropy is just minus the information, so we can write the expression shown at the top left of this slide. In addition, we have derived our expression for the probability of being in a microstate using the method of Lagrange multipliers. This expression is shown again here. If we take logarithms of both sides of this equation, we get the following. We can then insert the logarithm of the probability of being in microstate I into our expression for the entropy at the top of the slide. When we do this, we get the results shown here. Our next two steps in simplifying this result will be as follows. We will first change the order of the summations in the first term. We will then bring the factor of psi outside of the second sum, as this does not depend on the index that we are summing over. When these two things are done, we get to the following result. We now note that the summation in the second of these terms is simply equal to 1, and that the sum over I in the first term is equal to the average value for b superscript k. We thus get to the final result shown in the bottom right-hand corner of this slide. To summarize then, we have arrived at the following two results for the entropy in statistical mechanics by noting that the entropy is equal to minus the information. If our distribution is uniform, we have the result that is written on Boltzmann's grave. The entropy is proportional to the logarithm of the number of accessible states. In the more general case, meanwhile, when we have constraints on the average values of our extensive variables, the entropy is given by the expression shown at the bottom of this slide. I hope it is clear how we got to these results, but if it is not, please watch the video again and see if you can make sense of it on the second time through. Thank you for your attention.